Hello and welcome to podcast number 15, I believe it is. These are sort of zipping along, but just to let you know, this is based on near the start of chapter 4. So we went into alkenes last time, alkenes and cycloalkanes and unison saturation. This time we're going to look at actual structures. So we've so far looked at the side view, the dash wedge perspective, looked at the top view, the Fisher perspective, the Fisher projection. And this time we're going to start with the Newman projection, the Newman perspective. So we've done side and top. This is going to be a front perspective. And just like with Fisher, it's going to seem weird at first, but it's one of those topics where you do it a few times, you write a few of these out, and you start seeing a pattern, and it gets really easy eventually. Not at first, but eventually. So hang in there, do the best you can on these. And again, as with every video, if you need to, slow it down, replay things, speed through areas that you want to, you make the call. So I want to start with a relatively simple molecule, and that's going to be no more than 4 carbons to begin with. So we're going to look at 4 carbon species and 2 carbon species and make it simple, and then we'll build from there. So in this one, it's based on the visual perspective looking straight down a carbon-carbon bond, meaning the front molecule. So I've chosen butane in this case. So just to double check, 1 carbon, 2 carbon, 3 carbons, and 4 carbons. I've arbitrarily decided we're going to look down the carbon 2 to carbon 3 bond. So that's our visual perspective right there. So if we do that, you have these 2 H's, one in front, one in back, in this CH3 group sticking down in the front perspective, so they're close to your eye. And you have a CH3, an H, and an H far away. They're back. If you look perfectly down this carbon-carbon bond, this carbon in front is going to block, or if you will, eclipse carbon number 3. So I can physically see carbon 2, but carbon 3 has been blocked. So keeping in mind that's a perspective, and let me actually probably do that in a different color just to emphasize. I'm looking down to this bond right there. So I'll see this one sticking down in the front, this one up and back. Okay, so once you decide the orientation of what you're going to look for, you need to identify which is which. And so let me get rid of what I've drawn earlier. I want to really emphasize the following. So again, we're looking down this carbon-carbon bond. So this is the carbon I'm seeing in front. That's represented by this tiny dot you can barely see there. And this will become more distinct when I start adding substituents. But I'm putting my red cursor slightly below the dot. So right there, it should be right about on it. And then the back carbons were represented by this circle. So this represents a cone. So this point is the top of a cone, this is the back of the cone, and we're eclipsed. We can't see the carbon in back, so we just draw this circle. Okay, so again, on the front, I have altogether 3 things, and on the back, I have 3 things. So on the front, I have something coming up and out. So if I'm looking at it this way, that's going to be up and to the right. So I'm going to draw something from the center that's going to look like this. That'll be this one here. I'm going to draw something in back, like that. And then I'm going to draw something down. On the back carbon, I'm going to have something going down and coming out to the right side. But notice I start at the circle, not at the dot, because it's coming off the circle one. I'm also going to have this H in back doing the same thing. And notice this line would imaginarily go up like that. This line would imaginarily go like that to the center. And then finally, this CH3. Sorry, I want to switch colors. That one going up. So I have 1, 2, 3 on front, 1, 2, 3 on front, 1, 2, 3, 3 on back. Okay, I'm going to erase again my colors. I'm going to let the better graphic show it. But you have all together then 3 substituents in front, up to the left, up to the right, and down. 3 substituents in back, up, and then down, right, down, and to the left. So if you could somehow make an axis here and rotate it by 90 degrees, you get this perspective. So it's all in the perspective. So it is worth your time the first time you do this to color coordinate. So for instance, I want to draw these substituents let's say I start in back or in front, really makes no difference. I've arbitrarily decided to start in back. So I'm going to say this is my yellow CH3. So it's sticking straight up. And again, it's coming off the back carbon. I have my front, or not front, I should say, coming out from this perspective, H. It's still in back, but it's now on the right looking on this side. So that would be this H. And I have this H, which I'm going to say in back from this perspective. But in this case, it's going to be on the left. Okay, 3 more substituents to go. I have this CH3, which is going to be down here somewhere. I have this H in back from this perspective, so it's on the left, be around here. And then I have this H here, which is going to be somewhere in here. So hopefully my CH3, my back H, and my front H will all fit into place. So unfortunately, my 3 circles were off spacing wise. Shoot, I was hoping that'd be so cool if I would have done it right, but I didn't. So let me say the green again, the purple. No faith in me today. And then the black. Okay, perfect. So I've drawn the 3 substituents in back, yellow, blue, and red, check, and 3 in front, green, red, and purple, check. It's set. That is the perspective. So the front carbon is eclipsing the back carbon, so I see the front as a dot, I don't see anything in back, and then I just put the substituents on. Pretty straightforward. So if you do this and get it right, it would be time to do your little victory dance. But you can't see it because this is mostly audio and a computer screen of information, but I'm dancing. When I'm done dancing, it's time to move on. Steric hindrance. So I want to introduce this term. A whole bunch of different ways to think about it, but the best way to consider it is just 2 large objects cannot be in the same spot at the same time. So they will contort, twist, rotate, do whatever they need to do to get out of the same spot at the same time. So it's basically bulk interference, interference of one group with another. So if you're 3-dimensionally bulky as a group, you're going to interfere more than 2-dimensionally bulky, and in turn interfere more than like linear bulky. So steric hindrance is just the crowding of 2 groups trying to be in the same spot at the same time. So I'm going to take that same drawing we just did. I've changed it a little bit because before we had the one in front going down and the one in back going up. So it doesn't really matter. So instead of looking what before I called the carbon 2-3 bond, I'm now looking at 3-2 bond. It really doesn't matter. It's going to have the same implications. So if I spun this around, they would still be far apart from one another. So steric hindrance refers to how close these groups are. So if I look at this from the head-on position, they refer to the front carbon, the substituents, these 3. They are not blocking the view of the back ones, so they are not eclipsed. They're in between. So in between these 2 is this one, in between these 2 is this one, in between these 2 is this one. So we refer to it as a staggered conformation. Anti is going to refer to something eventually we'll know as anti-parallel, is that these 2 bulky groups, the 2 largest groups on the molecule, are in that plane. So they're in the same plane, but they're one's going up, one's going down. So they're planar, but they're opposite periplanar. So anti-periplanar, or short, we say anti. Anti is the best orientation to have 2 large groups. They're as far apart as possible, adds to stability. Okay, so how do we draw it? So I want to learn how to not only go from dash wedge, the stick figure drawings, to Newman, but I also need to go from Newman to stick figure. So important to know what's in the plane. So as mentioned, the CH3s, the 2 carbons, and the CH3 are in the plane. So CH3 in the plane comes down to this carbon in the plane, this carbon in the plane, and this carbon in the plane. Again, I want to emphasize, let me get rid of this drawing, the front carbon is going to be this carbon. So I decided we're going to look at it from this perspective again. You can pick either perspective, but I'm choosing to stay consistent and have my eye on the left. So with my eye on the left, There's my eyebrow, not a very good eyebrow. I'm looking at it this way. This carbon right here is in front. There's a CH3 coming up off of it. So there's my dot that's popped in. This one's planar up because it is straight up. Equally, this one right here is planar down. It's in the plane, but it's in back, so it's on the circle carbon. And then the front ones, this right front is down. It's going to be out and down. This one's left and down. It'll be in and down. Okay, so the front carbon, all taken care of. It's on that one. Back carbon, again, the back carbon we represent by the big circle. So that's this carbon right here. On it, we have, like I mentioned, the CH3 straight down and planar. So straight down is going to be planar. So planar down, straight down. This one is coming on the right, so it's going to be out. Again, it's on the back carbon. So right side is out, and then left side is in. So I'm going to erase my little add-ons and just hopefully emphasize that your front carbon is this dot, the back carbon is a circle. Off the dot carbon, there's a planar up, so a straight up. There's a left and down, which comes in and down. There's a right and down, which comes out and down. On the back carbon, the blue circle, you have a CH3 sticking straight down, planar and down. You have a left and up, which becomes an in and up, and a right and up, which becomes an out and up. All perspective. It's how you can rotate this thing in your mind. And again, it may not be a skill you have developed at this point, but given a few attempts, you'll master this. Okay, want to go back to the steric hindrance concept and say, yeah, anti is great, but occasionally they can rotate around. So sigma bonds, they're not limited by like a pi overlap. So pi bonds, you can't rotate around. They're locked in a position. But when it's sigma bonds and no rings, so it's completely aliphatic, no rings, no pi bonds, fully saturated, you're free to rotate. So this carbon here, this front carbon connected to the back carbon, that bond, we can visualize it rotating around it. Now I can rotate the front carbon, leave the back carbon in place, or I can visualize it leaving the front carbon in place and rotate the back, so almost like a steering wheel. So this back wheel, if we turn it, so I'm going to turn it in this direction, just the back one. So I'm going to use blue to emphasize that. So if this rotates, it's going to get in the way there, but if it keeps on going and ends there, that's not bad. So going from staggered to staggered, this one rotates up here, goes there, and this H will come down and rotate into that position. So if we do that, notice that this H is now down here, this H is now over here, and this CH3 is rotated up. So in your estimation, do you think it's better to have the CH3s as far apart as possible, or the so-called dihedral angle, this angle of rotation, being 60 degrees, meaning they're definitely closer together? Or if you said anti is more stable, absolutely true in terms of steric hindrance. We're going to learn that occasionally things want to be close when they have attractive forces, but steric hindrance is a repulsive force. So for steric hindrance, you want the two groups as far apart from one another as you can possibly get them. So staggered and anti is a better conformation, better alignment of the atoms than this one, which is going to be staggered because instead of everything back, but instead of calling it anti, and they're close together, we call it gauche. So the side view of that one, again, let's make sure we have everything translated correctly. On this front carbon, I have CH3 in the plane. I have H on the left, so it's going to be in. And I have this H on the right, so it's coming out. These here are no different than these here. They translate the same. In back, what's different now is I have the CH3 now going to the right, so it's going to come out and it's up. That one translates there. This H translates here, and this H translates here. The ability to draw one orientation compared to the other is going to be a pretty useful skill very quickly here. So straight up, planar up, as we mentioned. This one is out. So it's on the right and up, it's out and up. So I'm going to ignore the H's at this point. I'm just going to focus on the two interesting groups causing the steric hindrance. So one more alignment. Notice this one, you can now no longer see the back substituents clearly. They're blocked by the front ones. So rather than calling it staggered, we're going to call it eclipsed. And then a phrase that we'll learn when we start getting into reactivity of a molecule is when two things are blocking one another on neighboring carbons. They're referred to as syn. So anti, they're on opposite sides, but in the same plane. Syn, they're on the same side in the same plane. So syn offers high steric hindrance. Anti offers minimal steric hindrance. So notice that these are both in the plane and up, and these are both in the plane and up. So I'm going to, let's say, call this one my front carbon. So this is my front carbon, and the C3 back as such. So planar up in front, planar up is also in back. And then the H's are also coming out, going back, going back. Same thing here, left, left, right, right. Okay, this is your first sojourn into how to do Newman projections, so don't get too flustered, but hopefully it's pretty straightforward, and know that we're coming up, as always, with some new vocabulary for you to hang on to. Staggered, as opposed to eclipse, refers to the overall structure, and then gauche and anti refer to any two substituents you decide to focus on the neighboring carbon. So any front substituent and back substituent. I chose CH3 because they were notably larger than all the H's. So anti is when they're far apart, syn is where they block each other, gauche is where they're near each other, but still in staggered conformation. So the best option is staggered and anti, next best staggered and gauche, eclipse and syn is the worst. So it actually takes energy to go from staggered and anti to rotate this one 180 degrees around to get it blocked. So that means in solution at a given temperature, let's say room temperature, there's enough energy for everything to move around. So it isn't always in this form, it isn't always in this form, it isn't always in this form. These conformational isomers are constantly switching around, but the majority of the time, you're going to find it maybe 90% of the time here, 9% of the time here, and 1% everything else, including this really unstable one. So this is just a brief existence, barely happens. So want to look at that transformation from stable to unstable, how things move around. So I'm going to start with an energy diagram. And this energy diagram has on the x-axis the rotation around a Newman projection central bond. So for energy, I'm going to just start this case again. I want to start with a simple example. So I'm going to start with ethane, 2 carbons, 6 hydrogens. So here's the Newman projection. I'm going to say this is the front carbon, carbon 1. The circle is carbon 2, the back carbon. Everything has H's, but notice they are all across one another. So again, this is referred to as staggered, but there is no interesting substituent. So for instance, these two H's are gauche, these two are anti, these two are gauche. Every single H will have 2 gauches and 1 anti. This H, 2 gauches, 1 anti. This H here, 2 gauches, 1 anti. So everything is pretty much symmetric. This is going to be one of the more simplistic examples, but this is a stable form. So I'm going to start low in the energy diagram. And I've arbitrarily decided to consider this H in back and this H in front. I'm not going to go into why I picked anything. I just decided that's going to be my 0. When it rotates, when it goes up, I have to put energy in. So when it rotates 60 degrees, I'm going to have this situation where the back carbon is rotating again, like we did before. If I rotate it 60 degrees, this one will go here, this one will go here, and this one will go here. The problem with this arrangement is that in the end, you end up getting blockage, blockage, blockage. So it's said to be eclipsed. Notice the front substituents block the back substituents. This creates steric hindrance. If I keep on going another 60 degrees, so I'm going to move this one to here. This, hard to see, but the one in back is going to go there. One back is going to go there. So I'm now going to end up having it come back down. Notice it's the exact same energy because this H is no different than the other 2 H's. So where this H is anti and these 2 are gauche, or it's gauche, another one's anti, another one's gauche, makes no difference. So the energy diagram is the exact same level at that point. So really there's 2 extremes. There is staggered it turns into eclipse, it turns back into staggered. So as you probably expect, I turn another 180, I'm sorry, 60 for an overall total of 180, excuse me. It's gonna go there. This one's gonna go here. Go here, and guess what? It's eclipsed again. It's eclipsed where the red and pink are, or the pink and blue, excuse me, are coexisting in the same spot, or same positional thing from the front perspective. But whether it's this form or this form, it's still, H's are all roughly equal. When you start having groups that are not H's, this diagram will get a little funky. If I keep on going, I go back to staggered again, 240, I go up to 360 and it's eclipsed again, and back where I started after a full 360 rotation. So again, I've picked one of the most simplistic cases I can pick. In fact, the most simplistic. Everything is absolutely equal and symmetric. So you have 3 equal eclipse and 3 equal staggered, and it just goes from staggered to eclipse, back to staggered, back to eclipse, and so forth. So if you can visualize this, so if you can figure out what you're at, let's say when you're 30 degrees, you're kind of halfway between this one, staggered, and this one, eclipse. So your back ones are about 30 degrees off from being completely blocked. A few things to consider on this diagram while we're looking at this simple one before we get a little more complex. If you know the total energy, so let's say this is a certain number 2.4, and let's say this is a certain number 14.4, on some relative scale. The absolute numbers don't matter. 2.4 and 14.4 don't matter, but the difference between 14.4 and 2.4 is 12. So any way you cut it, you can call this 0, you can call this 2.4, call this 12. As long as go from 0 to 12, 2.4 to 14.4, 12 to 24, whatever it is, the difference is what we're always interested in. So in this case, if this is 0 joules and this is 12 joules, this is what we define as our 0 point, this is 12. There are 1, 2, 3 eclipse interactions between hydrogens. You go from everything being staggered, no eclipse interactions, to 1, 2, 3. So 12 joules difference and 3 interactions, that's 4 joules per interaction. So the 3 hydrogen-hydrogen eclipsing interactions are all said to have plus 4 joules for each of them. Okay. This is going to become not necessarily important, a strong word, but it's going to be something we reference down the road, is that eclipsing hydrogens are 4. If the group starts to get bigger, that number is going to get bigger. So if it turns into a massive multi-carbon substituent, that can go as high as 20, 30, something really, really large. And so these are the factors we're going to consider when we look at how stable the different forms are. It costs me 12 joules of energy to go up to this, but I get those 12 back, but I invested 12, and so forth. This is where we're going to pick up in the next video lecture. So this is that introduction. Make sure you understand the important things on this one. Gauche versus anti for the alignment of the key substituents I'm interested in a staggered conformation. Staggered as opposed to eclipse, staggered where you can see the back substituents, the view is not blocked by the front carbon, whereas in eclipse, the front ones block. So it is worth your time to label staggered, eclipse, staggered, eclipse, staggered, eclipse, staggered. Then you're done. And then as far as these go, anti, no name for it. Gauche, syn, gauche, no name for it. Anti. So it's terminology. Terminology is part of the growth process. And then just having an overall picture of how you're rotating and basically aligning molecules. So thank you as always for watching, and I hope to see you at the next video. Actually, I won't see you because I'm on the other end of a video, but you hopefully know what I'm talking about. Have a good day. Bye.